Have you ever wondered how data scientists can predict the future? Well, a big part of it comes down to understanding these two words, probability and likelihood. Now, it's easy to use these terms interchangeably, most people do, but it turns out they represent two very different but connected ideas that are essential for statistics. In this video, we're going to walk through a simple example to see how likelihood helps us learn from the past so we can then calculate the probability of the future. By the end, the difference will be crystal clear. Let's get started. Imagine we want to predict how many tornadoes will occur in a specific area next year. We know the outcome must be a whole number, 0, 1, 2, and so on. But weather is famously unpredictable, so we can't predict the exact number. The best we can do is to calculate the probability for each possible outcome. Fortunately, statisticians have already developed functions for common problems like this. The first step is typically to choose the function that best models our situation. For our tornado example, the Poisson function is a great fit. It calculates the probability of a specific number of events occurring based on an average rate, which is represented by the Greek letter lambda. Let's assume the average for our area is 4.12 tornadoes per year. Now we can begin calculating probabilities. Let's start by calculating the probability of having 0 tornadoes next year by plugging in 0 for x. The Poisson formula shows that it is 0.016. We can then repeat this calculation for every possible number of tornadoes. When we do, we generate what's known as a probability distribution. This can be visualized with a column chart, which is likely how you are used to thinking about distributions. As you can see, we can calculate the probability of future outcomes, but we first need a function that models our problem well and to know certain details specific to our problem. These details are known as parameters. In our tornado example, we had 1, which was lambda. But what if a parameter is unknown? We assumed lambda was 4.12, but there is no way we could omnisciently know the average number of tornadoes an area is destined to have. Without it, we can't calculate our probabilities. Therefore, we need some method for estimating them. We typically do this using historical data. Back to our example, we don't know the true value for lambda, so we need to estimate it. Let's say we observed 3 tornadoes last year. We can use this and our function to test possible values for the parameter. To start, we can plug in 1 as a possible value for lambda, and calculate a value of 0.061. We can even visualize it. This time, I will use a scatter plot. But does this mean that there is a 6.1% probability that the value of lambda is 1? No, because when you use the function in this fashion, using known historical data and a guess for a parameter, you are not calculating probability. You are calculating something called likelihood. It is best to think of likelihood as a score. To use it, you calculate the likelihood for several guesses for lambda. The larger the likelihood, the more likely it is to be the true parameter value. In fact, since lambda is an average, it can be a decimal, so we can try some fractional amounts. And since there are infinity decimal places, there are infinity possible values for lambda. So we'll ditch the scatter plot and replace it with a line. Once you have the likelihood calculated for several parameter values, the one with the largest likelihood is the most likely value of the parameter. This is called the maximum likelihood estimate, or MLE. In summary, we first use historical data to calculate the likelihood of certain parameter values. Once we have the most likely value, we use it to calculate the probability of future outcomes. Finally, what if you have multiple data points? For instance, what if instead of having only 1 year's worth of data, we observed 3, 2, and 5 tornadoes over the last 3 years respectively? To incorporate all of this information, you calculate the likelihood for each year's observations separately, and then multiply those values together. The result is known as the joint likelihood. While the calculation is different, the interpretation is the same. You still test various parameter values to find the one that yields the highest joint likelihood. The value remains your best guess for the parameter, the maximum likelihood estimate. It's easy to confuse probability and likelihood because they sound like synonyms and use the same formula, but they answer fundamentally different questions. First, we look to the past. We take our historical data, the outcomes we've already observed, and plug them into our function. This allows us to calculate the likelihood of different parameter values, helping us pinpoint the one that best explains our data, the maximum likelihood estimate. Then we turn to the future. With our best parameter estimate in hand, we use that same function to calculate the probability of all the possible outcomes that haven't happened yet. This two-step process sits at the heart of statistical modeling. Hopefully this video has helped make the difference clear.